force, work, and displacement. Let's start with a simple but confusing question. If we have a ball and we apply a force to it, and that ball travels to infinity, how much work have we done? Let's watch that animation again, but this time with labels. First, a force is applied to a stationary ball, causing it to accelerate. Then, the ball reaches a constant velocity and continues moving, eventually traveling off into infinity. As we know, work equals force multiplied by displacement. In this case, the displacement seems infinite because, according to Newton's first law, a body in motion will continue moving indefinitely. Also, force equals mass times acceleration. If the acceleration is constant and the mass is non-zero, then the product seems to suggest infinity. So, have we actually done infinite work? But if we look at the kinetic energy formula, it tells a different story. Work done is equal to the change in kinetic energy. Since we started from rest and reached a constant velocity, the total change in kinetic energy is half of mass times the final velocity squared. This is clearly not infinite. So, what is the actual work done? Is it infinite, or is it half of mass times velocity squared? Let's dissect this problem. First, a force is applied to an object at rest, which makes the mass start moving. That's because force equals mass times acceleration. Acceleration is simply the change in velocity per unit time. This means that the force causes the body to accelerate. And because of that acceleration, its velocity changes over time. Let's translate the situation into a graph. Here we have our ball at rest, and then a force is applied to it. After some time, it reaches a point where no more force is acting on it. At that moment, the acceleration becomes zero and the velocity stops changing. During the time when the force was applied, the ball covered a displacement s in time t. Once the force is removed, the ball keeps moving at a constant velocity. From that point onward, it will continue moving indefinitely, essentially traveling to infinity. So, what have we learned here? From the equations of motion, displacement equals initial velocity times time plus half of acceleration times time squared. Since the initial velocity is zero, the first term cancels out. Let's call this equation 1. Next, acceleration is the change in velocity over time, which gives us velocity equals acceleration times time. If we square that, we get velocity squared equals acceleration times time, whole squared. Let's call this equation 2. We also know that work is equal to force times displacement, and force is equal to mass times acceleration. Now, we can substitute the displacement from equation 1, and then substitute the squared velocity from equation 2, and we arrive at the formula for the change in kinetic energy. This confirms that our earlier conclusion was correct. To sum it up, when calculating work as force times displacement, we only consider the distance traveled while the force is being applied, not the entire distance the object travels afterward. So, the work done is not infinite,